Cool. All right. So this is the first chapter and everything, but in his solution set, I'm going to close the solution set for now. He has the numbers of the ones he has solutions for, so we'll work off of those. So that means in
Okay.
14.1, we start with number 7. So this is the start of this stuff. This is how we started when we first learned iterated integrals, and this is just us essentially just evaluating them. There's no manipulation, no special tricks. It's simply just going to be us evaluating. So you start by evaluating this function by x, which essentially you would just treat this as 1 over 1 plus x, because the y's are treated as an arbitrary constant when they're not being directly integrated. So I just replace them with 1s in my head. So the integral of 1 over 1 plus x wasn't that just what, ln of 1 or whatever or something? No, that's derivative
ln
of
of
something.
x.
Is it even that? No, when it's the integral, wait, negative, bring up to the top. Yeah, it's going to be an ln set. So isn't it the ln of the term below, right? So it would be ln 1 plus x, or is it something different?
Yes, but I think we need to do oh, this is just an ln function. It's an ln of
1 plus
absolute
xy.
value of xy.
And then that y on top can
xy plus 1.
Yeah, that y on top, since we're treating it as a constant, can technically be pulled out to the front and then multiplied across to the next term. So it'd be y ln 1 plus xy, right?
Technically, no, because if you're doing it that way, then we need to do u sub, since x is multiplied by an arbitrary x is multiplied by a constant y.
Yeah.
But if you think about it that way, then the numerator is just going to be the derivative of the denominator, and so with the natural log. Because if you put the denominator in a natural log function, it's just going to do, if you take the derivative, it's just going to put a y on top.
Oh yeah. So now I see it. So it's actually better in these instances not to replace it with a 1 in your head, but some arbitrary constant like 2, because then you'd see that immediately. Because if it, my battery's running low, I forgot to plug it in. I gotta do that real quick. All right, so then in this case, our derivative or our integral is just ln of 1 plus xy.
Yep.
Yeah, and then we have
technically
to
it's the absolute value. Yeah.
Yeah, so 1, 0.
And
then we have ln 1 plus xy evaluated from 0 to 1. So you plug in 0, it's ln of 1, which what, that's 0? No, that's tricky. That's going to be ln of, no, that would be ln of 1 if you plug in 0.
Yeah. You plug in 0, it'll be an ln of 1, and ln of 1 is 0.
Yeah, so that goes away. You plug in 1, and you will have ln of 1 plus y, which is what this is going to be, I guess. So that's that. So now we go on and we take the integral 0, 1 of ln 1 plus y evaluated, and that'll be evaluated later with respect to y.
You know what this is?
The big one with the cosines and stuff, or no?
If you want to, you can do it that way, or it's integration by parts.
All right, let's look at it then. So let's do integration by parts then, since that's something more people are probably familiar with as opposed to just the general solution if you just memorize it.
Yeah.
So integration by parts here. So we only have, ln of 1 plus y. So what are we going to select as our u term then?
1.
Yep, that makes sense.
Well, u is, we're taking the derivative of ln y plus 1, and we're taking the integral of 1, or dy in this case.
Yeah. So obviously, so when it comes to partial, it's, what is it? It's uv minus v du, or integral of v du. That's the formula for integration by parts. uv minus the integral of v du. So, so in this case, that means we select our v as 1 and our u as ln then? because then if we select u to be 1, no, we want v to be, we want u to be the ln function. So we would have ln of 1 plus y times v, which we'll pick as what, dy here?
Yeah, dv, yeah. We have u dv. So we got to take out u, which is natural log of y plus 1, and dv, which is dy. And then
When it comes to the dv part, does dy become 1 or do we leave it as dy there?
I don't think it matters.
Yeah, so I'll just leave that there. Dy. And then it is minus the integral of v, which we defined as the dy part. Yeah. So the integral of dy is then what? What would we say it's then there? Integration tree. Du, that's easy. That's just going to be 1 over 1 plus y.
Yeah. So our integral should be y over y plus 1, right? Or did I do something that?
If we picked v, so if dv, so you said dv equal to dy, so v is equal to y.
Yes.
Okay.
And then so we get minus the integral of v du.
Yes, so that would be y over 1 plus y. So that we have to take the integral of that then.
And that is just u sub. Where u is equal to 1 plus y,
Yeah, du is going to
du
be
equals dy. And then we get, what is it? U minus 1 over u. Yep. The integral of u is oh, that is cursed.
when you find a cursed one.
Well, it's more of just like I got the natural log of y plus 1 times y minus y plus the natural log of y plus 1.
Yeah, it's a little wucky. So let's see if we're even remotely close or if we just overcomplicate it. What did he do here? Did he use?
He used u sub. He
I
used u sub.
Is that a no, is this? No, it looks like, no, what did he do over here though? So he took this, he just defined that, yeah, dy, then he went around. He readjusted.
Oh no, he did what we did.
Okay, yeah.
He did what we did. That little box to the right is integration by parts.
Yeah. So he ended up with ln of
But he
w,
just,
which is what we ended up with, dw on that part, on that side. And then he got w times ln of w minus w, which should be what we have.
but I got plus ln of. Oh.
Yeah, so I suppose a good thing to do is refresh integration skills for this test, looks like.
Yeah.
These are the types of examples he has.
The thing that he did that we probably should have done is he did u sub again with w.
Yeah, he also modified his, he didn't want to change it back, it looks like, so he modified his limits of integration. As opposed, I never liked modifying the limits of integration. I would always replug it in at the end and then just use the originals, but it is more efficient. Yeah, so he just re-evaluated that function. He got that, and then he evaluated there.
Wait.
And he just got 2 ln 2 minus 1. So during his partial, he did ln w dw. So he did a u sub at the beginning to
We
simplify
get
it.
the same answer.
Yeah. He just did a u sub earlier to make it easier, which I guess is
We
probably
get the same answer if we plug it in.
Yeah, so that's good. Yeah. Oh, well, so that's how that's to be done. Yeet. Tricky. So that was number 7. The
Yeah,
next
that was
one.
integration by part. Yeah.
So this one's done by integration by parts when you get to the second portion. This one looks fun. Let's see. This one might be easy. We'll see. It's an e function, which is a little Bert, but let's see. Well, so number 9 is the next one on his marked. Yeah, so we'll do number 9 now. On number 9, we have 0 ln 2 1 ln 5 of e2x plus y dy dx. So we start with y this time. So we treat x as the arbitrary constant. So looking at this, the integral of e to the x is normally just, well, if the derivative of e to the x is e to the x, then the integral of e to the x is e to the x, right? But this time it's not as simple as that because the e to the x is something. So we would treat it for the first portion.
That's why we need to use
u sub, right?
Yeah, we need to use u sub, but we're going to treat it in u sub as x as a constant.
Yeah, so what we do is we do u is equal to 2x plus y, du is equal to dy.
dy.
Yeah. So then plug that in and you'll have e to the u du. You know, you integrate that and it's going to be the same exact thing. Because that's how this works. Then you'll have e to the u evaluated by 1 to ln 5. Now we could either, now right here we could do,
or we can do this a different way.
which way would you like?
We can use the multiplication rule of powers to say that e to the 2x plus y equals the same as e to the 2x times e to the y.
Does that help?
And then treat e to the 2x. Yeah, because e to the 2x is just constant.
Yeah,
so
right.
we're left with e to the y dy.
Oh, that's really easy too.
And that way substitution will be easier at this point.
Yeah, you're right. We'll do it that way. All right, that's better. So then instead, we can say it's e to the 2x times e to the y evaluated at 1 ln 5. If you take the integral of this, it just ends up being the same exact thing, right? Because if e to the 2x is a constant, it's pulled out to the front. The derivative of e to the x, or in this case, e to the y, basically the same thing. It's just going to be, or the integral of it is going to be itself. So it'll stay e to the y.
Yep.
And you take that. So in this case, we can only evaluate the EY portion with these limits. So e to the 1 or e to the first is just 1. So that doesn't change anything about the problem. And e to the ln of 5 is 5. So we end up with e to the 2x times 5 minus e to the 2x times 1. So that's going to provide us with e, or 4e to the 2x net when you evaluate that integral totally. Is that what you found for that?
Wait, what?
Did you get 4e to the 2x, or did you get something different? For this first, it's not done yet.
Wouldn't it be 5e to the 2x minus e times e to the 2x? Because if you sub in 1 for y, it's e to the y. It's e to the 1.
Yeah, e to the first power should. Oh yeah, you're right. What is e to the 1? It's just
e to the 1. I multiplied it by the same, so I got e to the 2x plus 1. So I did the same thing we did at the beginning, but
yeah, so I messed up there. I treated it as if it was e to the 0. E to the 1 instead. Yeah, so then you would instead have, as you just said, 5e to the 2x minus e to the 2x plus 1.
Mm-hmm.
So 5e to the 2x minus e to the 2x plus 1 evaluated.
And we can split the integral up.
Again, further to have a bunch of stuff, one of them being a constant. Back, split it up again, and you'll have.
Yeah, so on the first one, you have 5 on the outside with the integration from ln of 2 to 0. And on the inside, you have e to the 2x dx. And then the next one you have is e to the 2x plus 1 dx with the same length of integration because we just split them up using the sum and difference properties of integrals.
Yeah. All right, so looking at
So
this.
then it's just u sub again.
Yeah, once more.
U equals 2x.
Let's pull up what this is meant to look like.
U.
That's what it's going to be.
2x. So I got 5/2. This is disgusting.
So the solution is, it looks like he did it the way that we just did it. And he had the same idea at the middle portion. It ended up being 5 minus e times e to the 2x. Which when he integrated that, all that happened was it ended up being 5 minus e, because that's all a constant, times e to the 2x over 2. Which makes sense, I suppose. Because if you were to take the derivative of e to the 2x, it would simply be 2 e to the 2x. Thereby, the integral of it would be divided by 2, or divided by the derivative of its power. So that's a simple trick that we didn't exactly know at the moment. But because of that, that means, yeah, so he does the trick where he does 2 ln 2 is actually equal to ln 4 to evaluate, and ends up with 3/2 times 5 minus e. So the 5 minus e portion just remained constant and pulled out to the front for the remainder of that. And then that divided by 2 he got from the second portion. So that was just the reason it got complex towards the end was we weren't fully aware of the fact that, the derivative of e to the 2x being 2 e to the 2x meant that the integral would be divided by the derivative, right? Because then instead of using like a u sub there, you can just say that it's basically just divided by its derivative.
Yeah.
Divided by its powers derivative
yeah.
for the integral. But yeah.
Yeah. Where I messed up is I didn't take out the 5 minus e.
Yeah, because
it as constant. Yeah. I tried to split it up, and I was like it got a little messy, but I could have done it better. But
so it looks like that this test is just going to be just review your integration for the most part.
Yeah, basically.
All right, and then the last one is that 21? Let's go down and look at it. Yeah, it's the same one. All right. All right then. 21 is by an area. So this is one that I need to get a better grasp of. So when we have x, y cubed over x squared plus 1, divide to the derivative of some area where r is given as 0, x, so x varies to 0 to 2, and y varies from 0 to, no, x varies from 0 to 1, and y varies from 0 to 2.
Okay, actually, these are kind of similar to the other problems where dA can be either dx dy or dy dx.
So we
So-
can arbitrarily pick.
Yes, so choose the one that will make it easier on you.
So looking at this,
Now-
it's obvious that the y should make it easier, right? If you pull out all that x stuff at the beginning, then your first integral would be easier.
Yes.
So you want to do it that way?
And then and then you get like a, yeah.
And then when you do
So-
it that way, does that mean that the first barrier or the first limits of integration are, you know, like if we're choosing to do y here, so does that mean it goes from 0 to 2 for the evaluation?
Yes, that's for the inside.
Yeah, that's okay.
It's forever with.
So let's check that out then. Let's try it. So if you pull out x squared plus 1 out the front as a constant, and then take the integral of that y cubed, you're simply just going to get y 4 over 4. Cool. And then you can evaluate the y 4 over 4 from 0 to 2. You 0 at the 0, put 2 in there, and it's going to be 2 to the 4th power. 2 to the 3rd is 8, so you're going to have 16 divided by 4 is 4. So now we have 4x over x squared plus 1. Evaluate and take the integral of that from 0 to 1 dx. So that's where we get to. So you go from there, take the integral of this function with respect to dx. So I'm looking at an x squared plus 1. Isn't that inverse tangent?
It's u sub again.
Yeah, I mean, yeah.
Take out 2 from the top and then.
Yeah, use
I
equal
mean,
to
you
x
can
squared.
do tricks if you want.
No, I would rather die.
I just would not recommend doing tricks.
Yeah, I would rather die. So
I would not recommend.
So then if you look at it, you can take a 2 out from the top. Yeah, or you can in the du, you can multiply du by 2. It's the same exact thing either way. So pull out a 2 for later on the outside of that integration, and you're going to have 1 over u. So we know that the derivative of 1 over something is ln u. So 2 from 0 to 1 of ln u, which ends up becoming 2 ln x squared plus 1. And then we would evaluate that. Now, do you want to make the 2, bring that over as a power of the total function, or save it for the end? It's probably easier to save for the end.
Just multiply it.
Yeah, much easier to just multiply it. So then evaluating this, if you put in 0, it's ln of 1, which is 0. If you put in 1, it's ln of 2. So we have 2 ln of 2 minus nothing, because ln of 1 is 0. Let's go see.
Yep.
Yay, it's 2 ln of 2. Yeet. All right. So that was all of his worked problems. Let's look over the remaining ones and see if there's any of these that are like markedly different, although I doubt it. So every single one of these is simply the same process. The process of iterated integration is the same across all of these. It's simply the type of integration that you've learned in the past calculuses that vary. So that's something that's good to review if you're not aware. When it comes to
If you're not dealing with it, treat it as a constant.
Yeah, when it comes to these ones, when we're evaluating double integrals over the given region R, as John said, you get to arbitrarily pick which order dy, dx, or dx dy you want based on whatever makes this easiest. So when we did 21, we selected y as our start. Therefore, we integrated the inner integral from 0 to 1 or 0 to 2 for y. That meant that we were allowed to take x over x squared plus 1 out to the front as a constant and do nothing with it till the second portion. So when it comes to these, you just pick whatever you think is easiest. And that's that. And then when it comes to these ones, let's look at this real quick. This looks a little different, but it probably is the same. Oh, wait, no, it's a little trickier. It's this one saying find the volume. So that's triple, right? Find the volume of the region bounded by the paraboloid z is equal to x squared plus y squared, and below the square, and then it gives you a region. Well, we know how to find the area.
No, this is actually, I think, just a double integral of z.
Yeah, because look, because if you find some paraboloid that, and then below the square, yeah, because we haven't gotten to triple integrals, right? Or even like we haven't gotten there yet.
Yeah.
So when it says find the volume of the region bounded, you simply do the double integral of that function. And what we get to the same trick here. We can just arbitrarily pick the order, even though this one's pretty easy.
Yeah.
Yeah. The other one is the same trick. Yeah.
Yeah. Because z is, it's a function in z, we can just do a double integral with dx and dy.
Okay, and then that's the same for 27. So that's all of 2-1. It's just introductory topic of double integrals and evaluating over an area, which we get to go.
And right now, it's
Fubini's theorem. Fubini's theorem is just reorganizing, like going to dy dx instead, right?
Yeah.
Okay. Even though he didn't say we had to do these for 1. Let's get over here. Oh boy, zip, zip, zip. Oh, you were gonna say something, Bert?
I have no idea.
All right, this one is, it looks like 13, 15, 17. So let's look at it. Oh boy, come on, where are you hiding? 13, 15, 17. So what is it asking? It starts up here. Write an iterated integral, and we're doing it over the area of the described region using vertical and horizontal cross sections. Okay. Let's look at this. So 13 is bounded by y is equal to root x, y is equal to 0, and x is equal to 9. So I suppose the first thing we should do is doodle this, visualize it. So we're only working with 2 axes here. Y is equal to 0 means we have a horizontal line. It's just the x-axis. X equal to 9 is a vertical line at x equals 9. So these are our bounds. And then y is equal to root x is, it didn't say plus or minus here, so it's literally just going to be, from the origin root x up until it intersects x equals 9. So our bounded area looks like a sideways half parabola in the first quadrant.
Something like this.
All right, so looking at this, if we want to write an iterated integral using vertical cross sections, that would mean what's changing, or vertical cross sections, the limits of integration for, so we get to pick the order here, but if we're gonna do vertical, I say we pick x is gonna be first, right? Because then if we're looking at vertical cross sections, our bounds is a constant bound of y equals 0, and then an upper bound of y is equal to root x. Because as you move along the, if you're taking vertical cross sections, the lines are going up and down.
If I'm right, if we take vertical cross sections, we need to have dx be second.
Dx be second, all right.
Because we're going to find the vertical cross section by dy, and then we're going to add up the vertical cross sections by dx.
Okay.
That makes sense.
So, all right, so then in that case, shouldn't it still be, the bound still be 0 to root x and then 0 to 9 for vertical?
Yes.
Yeah. So I just spoke wrong. The order was off there. So this iterated integral, the inner integral is your dy. So it's going to be 0 root x, because if you pick any arbitrary point in this area, let's like just pick in the middle somewhere, you're always going to start at your first bound, which is the x-axis, and it's going to be a value of 0. And then you're always going to end at your upper bound, which in this case is y is equal to root x. So it's going to be the function as opposed to a value. And then when we start evaluating the next portion, it's going to go from 0 to 9, because that's how the x-axis varies. And this is going to be, isn't this the first one where it literally is just like of dy dx, like there's no inner function?
I believe so.
Yeah, in this case, there's no inner functions for these ones. Because what's happening is you're actually creating a function as you integrate. Because your first integration, if you integrated this one, you're going to end up with, you know, root x, and then you integrate that, and that'll give you your area. Cool. All right, so the next one is horizontal, right? It's asking for horizontal cross sections. Cool. So this one's a little interesting, but not super different. Horizontal cross sections, if you're starting and looking horizontally, your lower bound will be your the root x function. But should we reevaluate that? Or should we replace it, or should we leave it as root x? Because if you're looking,
what would you turn it into?
Because what if you're looking at it from? Because when you're looking at horizontal, like we're trained to use we're trained to use Cartesian, like as like x is the like horizontal, y is the vertical. But if you're looking at it with horizontal cross sections, then from the perspective of the y-axis, who is now in place of the x-axis, the function's y squared, right?
Okay, yeah.
Yeah, so that's what we would do. We'd reevaluate it here. So instead, yeah, horizontally, your lower bound is going to be y squared, and your upper bound is going to remain x equals 9. Or it's going to be x equals 9 to start here, right? So in this one, it's going to be y squared. Luckily, we have the answers for these, so we can check afterwards. Y squared to 9. And then the next part is the intersection, which should be 3, right? The intersection. So the next integral, and this one's, isn't this one dx dy then? Because we flipped it.
Yeah.
Yeah. So this next portion, I think so. I'm pretty sure it should be. Otherwise, yeah, it should be. So then if we're going from y squared to 9, then our next one is going to, looking from that orientation, is going to be how it varied along the y-axis, which varied from 0. So our lower bound will be 0 to how it varied
the
from
intersection of
yeah,
x
the
equals
intersection
9
of
and
the
y
function.
equals x equals square root of x. So we plug in 9 for y equals square root of x, so we get 3.
Yeah, at the upper bound should be 3. So that's, yep. So that's what that should be. Let's check it. That is not it. This is it. I gotta zoom in. Yeah, look, we were right, but he didn't write this. He didn't write if it's dx dy down here. So that's what I'm interested. Does it change or does it stay the same?
Well, we're going to get an integral in terms of y for the first integration, so we need to integrate it again to get it in respect to the ui. So we have to integrate it with dx first because one of our bounds is in y.
Yeah, see, so I guess he's just like this is just introducing the idea of flipping them like that. So yeah, so and this idea, this topic from 14.1 is what just gets dragged along and expanded upon with a third dimension in later on when we start doing the triple integrals. So it's basically what it is. Just reevaluating and Fubini's theorem, all these things just get piled on together.
Yep.
So,
good old Fubini.
yeah, exactly. All right, so these are pretty quick. So let's just do the other 2 real quick. It's 15 and 17 left. So if we're bounded by y is equal to e to the negative x, y is equal to 1, and x is equal to ln of 3. Funny. All right, Cartesian. Boop, boop. All right, so
Boop, boop.
so e to the negative x is an inverted. So e to the x is like just a super exponential, but e to the negative x
It's just like it's just
super
gonna be like it's gonna
reverse it, right? Should it just flip it across the axis, right? Because if you're looking, because e to the, I actually have a lot of experience with e to the x functions because of solid state fundamentals. The formulas use them all the time. So what happens is e to the x, your thing on the negative side almost immediately approaches 0 the larger the negative number is, and it never hits 0, it just approaches it, and then the moment you go positive, it like almost like hits big boy numbers super quick. So then if it's e to the negative x, you invert that. Any negative value is going to become a massive positive value very quickly, and then any positive value is going to approach 0 almost immediately. So it's simply flipped across the y-axis when it's e to the negative x. So I guess for this stuff, it's also extremely important to know what graphs of certain functions look like in order to actually succeed in these problems, because if you can't draw it, you'll probably struggle a little bit more to visualize it. Obviously, we get to a value y is equal
Here
to
is 1 over e to the x. Here's 1 over e to the x graphed in my graphing calculator.
Did you flip it?
I figured.
Does it look
What?
like e to the x flipped across?
Well, we can look at that.
Here, let's see. I'll go to.
Why do you not like me? Do I have a variable?
Yeah, look, it's just flipped. I went to Desmos.
Yeah.
Yeah, that's what it should look like. All right, good. We were over here. All right, so there's that one. Next formula or next thing it gave us is y is equal to 1. So that is a horizontal line at 1. Okay. And then we have x is equal to ln 3. What is ln 3's numerical value? Ln of 3. It looks like it's basically 1. So we'll do that then. This looks super tiny. This is a very small area. Either way, it doesn't mean we get to slack on it. All right, because of that, I'm looking at this doodle. And for the first one, our iterated integral, if we're using horizontal, that means that we should start with a lower bound of y is equal, or just e to the negative x, and an upper bound of 1, because it hits the y is equal to 1. Then for the next one, that means iterating across or integrating across that remaining dimension, which is going to be the x-axis, our limit being 0 to ln 3. Which works out because that looks like, and then this would be what, dy dx. So it looks like when we're working areas, a vertical is always dy dx and a horizontal is always dx dy. Doesn't look like there's much variance there. Then the next set would be a double integral. If we're looking vertical now, our lower bound is what? It's the reevaluated. The lower bound, as we figured out last time, is your like that function. Like last time it was y is equal to root x. This time it's y is equal to e to the negative x, reevaluated to where it's the opposite variable. So in this case, what we would take ln of both sides. You'd have ln y is equal to negative x, and then divide by a negative, and you'll have x is equal to negative ln y. So our lower bound is negative ln y. Our upper bound is still 1. Wait. Yeah, our upper bound should still be 1. And then our sideways bounds go from 0. Oh, wait, no. Ooh, almost messed that up. Our upper bound is not 1. In fact, our upper bound is ln 3. And then our bound across the second integral should go from the intersection, oh boy, the intersection of negative ln y with ln 3. So it ends up being ln 3. Wait, I don't even know what's happening anymore. ln 3 is equal to, is it the upper bound or the lower bound? So it's negative ln y's are lower because that's the reevaluated e to the negative x. Looking this way, and then our upper bound. Wait, no, our upper bound should still be ln 3. Yeah, that's correct. Because that's constant. What isn't constant is our next level, which will be the intersection of 1 with negative ln y, but ln of 1 is 0. So 0 is it 0? Right. Shouldn't
Okay.
be lower 0. Have you figured out yet? I'm having some trouble visualizing the second one.
Okay. So what did you do first? What did you do first? The horizontal or vertical?
Vertical to
cross-section?
start. So dy dx. And I got no lower bound of e to the negative x, upper bound of 1. Next one is 0 to ln 3.
Okay, yeah, that's what I got.
Yeah.
And then you said horizontal next now?
Yeah. Horizontal comes next.
Okay. So we go into the function of e to the negative y and we leave the function at ln of 3. But we're going to have it
How'd you get it
in
to e to the negative y?
e to y equals e to the negative x, sorry.
Yeah.
So we have to solve for x in this case
Yeah, so that's what, negative
because we
ln
are
y?
then going to sum up all the
Yeah.
So
okay.
it's negative natural log of y is the bottom, and then the top is natural log of 3.
Yeah, so I have
And
that part.
then
Now the second part's a bit trickier.
so we look up the intersections between x equals natural log of 3 and y equals e to the negative x in terms of y. So at that point, we just plug negative ln 3 in for e to the negative x. And let's just go ahead and drop e to the x down in the denominator so we can sub in ln 3. So the ln 3 cancels with the e. So e to the negative e to ln 3 is just 3. So our bottom is going to be 1/3.
Okay.
And then to find the intersection between y equals e to the negative 1 and y equals 1, we then solve 1 equals e to the negative x. And
shouldn't it just be, so looking at this, when you do your upper, so I understand the lower is a little tricky because it's like the intersection there, but the other one, doesn't it approach a constant value across that? Like it's gonna intersect at y is equal to 1, right?
yeah.
Yeah.
Yeah,
So
and that's the point. Yeah, I'm sorry. Yeah.
Yeah. So for that
I
one,
tried to make it
for the lower one, you do in fact have to solve, but for the upper one, in the case like here, when it's a constant line, it's just gonna hit that value.
Yeah.
Yeah. So let's check, but I'm
I
pretty
tried to
sure.
solve for it. We didn't need to solve for it. Yeah.
Yeah. So we have negative. Yep, that's right. That's right. And then yep. Then that's all correct. And yeah, and here he did do dx dy. So yeah. So it flips. It's always if it's vertical, like traditional integration, dy dx, and if it's horizontal, it's dx dy. It just flips. So the last one is 17. So we can quickly run that one. This one's a bunch of linear functions. I doubt there'll be much issue here. So 17, drawing the sketch. So it looks like for these ones, one of the most important things that you need to know how to do is to sketch them out. Because without drawing the sketch, it really complicates understanding it and it'll make it a lot harder. He also may give you a sketch. So if he gives a sketch, I guess that helps, does a lot of the work for us. So y equals 3
And
is
I
a
think he
horizontal.
said he wouldn't give us too many. He will give us a sketch for a lot of the 3D at least. Probably not a lot of the 2D.
Yeah, 2D ones are probably just going to be us sketching them on our own for our own uses. Doubt it'll be graded on your sketch or anything. All right, so this first one's y is equal to 3 minus 2x. So what? That's a y-intercept at 3. Y-intercept at 3, and then you just go down. It's rise over run. So you go down 2 over 1. So it's just a line. It's just a linear line. So you just plot that. Data has to be specific. You just need to know the formula. Y equals x, everyone's favorite 45-degree function. and then x equals 0. Well, when x is equal to 0, that's just the y-axis. So we have a triangle area here. So that'll be fun. To start, we're doing vertical, so we're working dy dx. Our lower bound here, what the hell's text? Our lower bound here is going to be, in this case, it's going to be y is equal to x, the function y equals x. So we're going to have x as our lower bound. Our upper bound is going to be the function y is equal to 3 minus 2x. So then our upper bound is 3 minus 2x. And then our next portion, evaluating across, is going to go from 0 to the intersection of our two functions. So where do these end up intersecting is the question. So if y is equal to x, if you set x is equal to 3 minus 2x, you plus the 2x, you're going to have 3x is equal to 3, divide that x is equal to 1, it intersects at x equals 1, so it's going from 0 to 1. You get that? For this part. This is the vertical dy dx portion.
dy dx. Yes. So we're looking for what? The y coordinate of the intersection to figure out
yeah, x coordinate here. This is the second portion. So the first part, I have lower bound as y equals x, upper bound as y is equal to 3 minus 2x. And then, because since we're moving vertical, you start by going from top, like bottom to top. And then for these questions, when you're doing vertical, your next portion is going from like along the x-axis. So you start by going along the y-axis, then you start by next one's along the x-axis for your area. So for the second part, your lower bound is just x equals 0, or yeah, your lower bound is x equals 0. And then your upper bound is the intersection of the two previous functions, which happens to be x equals 1. You simply set those equal, and it's a pretty easy algebra solve. And you just get 1. So that's what I have for that part. And then yeah. Ooh. All right, so there's that one. I'm looking at it, and I have a feeling that this next one is going to be a bit interesting. This next portion, the horizontal one. All right.
Horizontal one?
Yeah, so we just did the vertical. Now I have a feeling that the horizontal one is going to be a bit interesting because it's a triangle. So horizontal.
We probably need to split it up, right?
Yeah, that's what I'm thinking. I'm thinking we're going to need to at the intersection point, it's going to be split down into two separate functions.
Yeah, so we need two different separate intervals.
Yeah. So but
So
I wonder how we do that though for these ones. I guess this is an interesting test case. So
we would just add the two together.
Yeah.
Treat it as two separate intervals.
Yeah.
So what that means is we take the bottom half, which is between
y equals x to the intersection, which is at x equals 1.
Yeah,
so it would be,
what is that intersection?
That intersection, if x is equal to 1, then you can rewrite that as a horizontal line at y is equal to, oh shit, yeah, you're right. We're gonna have to solve for that intersection's y component. So we can evaluate either function. We know that y equals x is one of the functions here. Therefore, if x is equal to 1, y is equal to 1. So this means that we can draw a horizontal line across, and that splits the triangle into two portions, where the upper portion is bounded at the top by 3 minus 2x, and the lower portion is bounded by the bottom at y equals x. And each respective portion has a lower and upper bound of 1. So we're creating two separate triangles here. So, okay, that's cool, actually. This is an interesting one. I hope this one's on the test. This one's a really interesting test of just like logic skills as far as I'm concerned. So if that's the case, then as you said earlier, we're going to write two separate integrals where we just integrate across two triangles, both of them horizontally. So starting,
Yes.
so these are all going to be dx dy's. So
Yeah.
we would start, and the
So,
first one would be
so we go in at 0 for both of them, right?
yeah. So the first integrand is going, or the first bound for both one's going to start at 0. So you'll have, and I think for both of them you just write dx dy for both.
Yes.
So dx dy
Yes.
dx dy. So both of them will start at lower bound of 0, but they'll have a different upper bound. And remember, it has to be redefined as a y function, or as a function of
Mhm.
y. So for our top triangle, our upper bound is going to be what? So it's going to be, subtract 3. So y minus 3 divided by -2 across the board. So negative y, or negative y over 2 plus 3 halves. So negative y over 2 plus 3 halves is that function. And then the other one is just y equals x. You flip it, it's just x equals y. So in this case, it's just y. And then the second integrand for each one is why we split it up too. It's going to be a little bit different here. So this is where the 1 comes in. So if we're looking at the top triangle, the lower bound is 1, and the upper bound, oh damn, what would we say the upper bound is here? We don't have a numerical upper bound, do we? So we evaluated horizontally, so we had to reestablish that. Oh wait, no, yeah, okay, I understand now. So our upper bound for this triangular set is then going to be the intersection of the function. It's y-intercept. It's going to be 3. It's the intersection of the upper triangle's top function, which is 3 minus 2x at x equals 0, which is just the y-intercept being 3. Because our second integrand, our second iterated integral always has to be numbers here. It can't just be another function. And then the difference is the next triangle, our upper bound is 1 as opposed to it being the lower bound. And then it has its integration at the origin, which is 0. So our overall answer here is going to be the integration from 0 to, actually not here. Instead of reading it out, we're going to check the solution and see if we got it right. Did he even finish writing it? Oh, he did. He wrote them here and just redefined it. Is equal to I1 plus I2. So here, let's check. So our first one, our upper triangle, as we spoke about it, 0 to 3 halves minus y over 2. Yep. 1 to 3. Yep. Next one, 0 to y, 0 to 1. Yep. Okay. Cool. All right. So these ones are as long as you understand what the question's asking in terms of what to actually do here, these questions I would say are less involved and probably easier as long as you know how to draw the graph than this one. This one seems deceptively easy because it's a bunch of linear functions, but it's actually relatively complex when you get to the second portion because you actually have to break up the integral geometrically and evaluate it as 2.
Yeah.
So these ones
I
are
gotta slow down on a lot of these
yeah. Sometimes you
because
overspeed and make a mistake, which is
yeah,
not what you want to do on tests.
because I just start freaking out and then I'm just like, let's calm down. In versus out, and then you write the bounds in between.
It's all about the
2
bounds.
points.
This entire test is about the bounds. It's all about the bounds.
Literally.
Basically, yeah.
All of this
because we're
basic integration and writing bounds.
we're no
what this
longer at the portion where they care about the 14.1 is where they want you to write bounds for where they want you to integrate actual specific functions. Now you're just integrating dy and dx with respect to weird ass bounds, and it just so happens that one of the bounds always end up making a function for the next level.
Yeah.
All right, so that's all of 14.2. So let's check 14.3's. There's a bunch of questions in 14.3, it looks like, so we'll have to pick a subset that we feel we should look at. So what is the list of them? We're looking at 3, 5, 7, 9, 13, 15. So it looks like you just add 2, except for when we get to 21. So that's what we'll do. So it started at
It
3.
looks like he also did 1, did he not?
He did
Yeah.
1, but he didn't put it in as one of the questions in his solution. So cool. It's 14.3. So we will look at this and see what it's asking. So he circled them all for us too. So he has solutions for all of these -11 and 13. So we can pick like 2 or 3 of these to do since we're not like made of time. The coordinates axes, so let's look. So it's asking, sketch the region bounded by the given lines and curves, then express the region's area as an iterated double integral and evaluate the integral. So I feel like we just did this, but doesn't hurt to do it a little different if so demanded. So the coordinate axes, easy, and some line. Okay, so this is interesting. So he's giving us a function that isn't expressly defined in terms of either at the beginning. So we can, this one I feel is interesting because we can, this simplifies it a little bit. Because you just set equal. So,
And
he doesn't say vertical or horizontal here. He just basically tells you pick one, right? Because I feel like what 14.2, the whole point of that chapter and that topic is to like show off Fubini's theorem, that type of stuff, and show that you can choose how to integrate across by an area either way, whichever you feel is easier to you. I feel like most people will still pick vertical just because of old habits, but horizontal can sometimes be easier. I understand that it really just depends what the graph looks like. So obviously he says sketch here, so we'll do the same. We'll just sketch. I say we probably do like 1, 5, and like 9 here, because these will probably be quick.
Yeah, okay, yeah.
Unless 13 is different. We'll look at 15. I mean, no, it was 13. We'll look at that one later. All right, so 1.
Yeah.
For
13,
the coordinate
15,
axes,
and 21.
the coordinate axes and x plus y is equal to 2. So just me, I'm going to do what I just said and stick with vertical. Thereby, I'm going to define this function by x and say y is equal to 2 minus x. Therefore, our y-intercept is 2, and it's simply going down by 1 each time, each increment of x. So we create a right triangle, a handy little right triangle here, because also this is bounded by the axes. So this shouldn't be too bad. Integrating this, a double integral. Well, you start with a lower bound of 0 and an upper bound of y is equal to, so it's just gonna be 2 minus x.
Yep.
And that's dy, dx, and then the next one dx. Your lower bound, once more, you're going to start at 0, and you're going to go to the intersection, which happens to be at x equals 2 when it reaches 0.
Yeah.
So that one's done. So these ones are illustrating how much faster it is, as opposed to having to write 2, which are actually just going to give you the same answer anyway. When you get to pick one, then you can immediately write these things out and solve them very quickly. And then it says express the region's area as an integrated double integral and evaluate the integral. So I guess we can just quickly evaluate this one. So this is going to produce the function 2 minus x, and then you integrate that. It's going to be 2x minus x squared over 2, and then you plug in 0, all that goes away. Plug in 2, you're going to have 4 minus 2 is equal to 2. So the overall answer I have for 1 is 2. Look. Did he not even evaluate? I don't think he evaluated.
Wait, what did you get?
I got 2. That might be off.
Wait,
I went a little quickly.
So from the region I got 0 to 2 minus x, right? That's our inner.
Yes.
So our integral is 2 minus x. And then, oh, I didn't take the integral. It helps if you take the integral of it.
Yeah. You got to take the integral, which produces 2x minus x squared over 2. And then you plug that 2 times 2 is 4 minus 4 over 2, which is 2 again. 4 minus 2 is 2. Yeah, that's something. So that's something because in the past, the last one we didn't do any evaluating, but it's because I feel like the trick here is like everyone gets tripped up there because the first one there is no like numerical evaluation and actual integration. You just take your upper bound and multiply it by 1, then it's just itself. But it's good to remember the second portion is in fact integration. But either way, either way, he didn't evaluate it in his solutions, but I'm pretty sure we both know how to do the integration of that, and I got the answer too. And once you integrate it, I'm sure you got the same. All right.
Yeah.
Let's just.
What I went.
you want to do number 3, which is another, looks like a linear one with like a y squared, or would you rather do 5 because it has an e to the x and it might be fun?
Well, let's go 5 because that
E to the x time.
we can do. Yeah, let's do 5. It's more fun.
Yeah, it's better to show off because I'm sure everyone understands how to do linear and quadratic function ones. Those are not as
Yeah.
tricky. People get tripped
As
up.
always,
So,
I'd rather have someone teach me how to do the hard ones and then do the easy ones by myself
yeah.
instead of having to do the easy ones
Yeah.
in class and then.
Yeah, it looks like a big thing about these problems is actually, as you said, everything's about sketching and understanding the area here. So like in the first one, he says the coordinate axes and the line x plus y equals 2. But in this one, it doesn't say coordinate axes, but y equals 0 and x equals 0 are the respective coordinate axes. So it still has them. They're just being described in a different way. So it's good to understand those types of descriptions because if you don't understand one of the curves or one of the lines that are your bounds for your figure, that's going to mess up your answer, even if you do everything correctly. Y equals e to the x is the traditional e to the x function. And then we have an x equals ln2, so a vertical line at ln2. I don't know what that value is. I don't actually need to know what that value is. I'll just put an arbitrary
It's
vertical
about
line.
1.
Yeah, ln3 was a little
No.
over 1. So ln2.
Okay, then ln2 is a little less.
Yeah,
yeah, because a little less than 1.
Either way,
2.71828 is e.
Yeah, luckily for us, we really don't have to care because when it comes to the actual, numerical values of your figure, it doesn't matter. You simply need to see the figure itself. And this one looks like a relatively small area as well. So looking at this, actually, it could be bigger because E grows pretty damn fast. All right, well, yet again, this one looks pretty easy to do vertically. So I'm going to do a dy dx portion. That's how this one is going to go.
Yeah.
So
always try to do something that doesn't make you do 2 integrals. Always try to do something to make sure you don't have to do 2 integrals.
Yeah,
like if we did this horizontally, we would have to do 2 integrals.
Yeah, when we have to break it apart or something like that.
Yeah.
Yeah, we would have
to. So
always
try to pick something where you don't have to break it apart.
Yeah, because if we did this one horizontally, it would produce 2 figures. One where e to the x intercepts the y-axis, and then another where below that where you have a rectangular shape.
Yeah.
Yeah, that's tricky. I don't want to do that. Avoid that at all costs, unless required to do so. So this one, doing this vertically, our lower bound starts 0. Our upper bound is just the e to the x. Yeah, e to the x. And then our bounds from the side is yet again, looks like it's just going to start at 0 and go to ln3. No, ln2. I'm messing up. I'm thinking about the last problem we did ln with. And I wrote 3 again after I erased it. 2. There we go. All right. So evaluate this. You just throw in the top of the first. So you have an e to the x. Evaluate that. We know the integral of e to the x is e to the x. Same exact thing. Evaluate that from 0. So this one's actually going to have a -1 in it because e to the 0 is 1. So evaluate this, but it's not because it's going to produce a number, ln2. So if you have e to the ln2, you get 2 minus e to the 0th, which is 1. So our answer is 1 overall. 2 minus 1 is 1.
That's what I got.
Let's see if he evaluated this one. He refused. No, wait, that's the wrong one. This one.
Yeah,
he refused. Yeah. Look, so that's what we mean by having. If you did this vertically, this is what we mean by you'd have to evaluate this 2 separate ways. Because vertically, you would have to draw a line across at this intersection to be a horizontal line to evaluate. If you did so vertically is what we've been doing, like you're in and out vertical. Yeah. If you chose to do this horizontally, as you said, this would make you do 2 integrals because there'd be a line that you'd have to cut here to take the integration up of this portion, and then you'd have to take the rectangle. You wouldn't have to take the integration of the rectangular portion. You could just do this distance times this distance. But it would still
natural log of 2.
Yeah, it would still it'd just be the natural log of 2. But even so, yeah, it would still be annoying to have to do that extra step when it's a little bit easier to do it the way that we just did. All right, so that's 5. Let's see if either of these have any special cases. Otherwise, we'll look at 13. Parabolas. It's still just pretty basic. At this point, this is just like learning how to like draw your parabolas.
Yeah.
Although you don't really need to know how to draw it perfectly. Although you can if you want. And when it comes to these functions, for the most part, unless it's something more complex like E or an ln function, you can simply insert numbers in your head and plot. This one, more linear. Yeah, more linear functions. More linear functions. All right, so we'll look at this and see what these are asking. The integrals and sums of integrals in exercises 13 through 18 give the areas of regions in the xy plane. Sketch. Okay, so this is asking us to sketch the region given the integral and then evaluate. Okay, so I guess we can just do 13 then and see, because if this is asked on the test, it might be a good idea to demonstrate how it's done. So the first things first is the most important thing to note is what reference we're using. At number 13, it's a dx dy, meaning this is a horizontal integration. Thereby, everything that was in terms of y or was in terms of x has been inverted and made in terms of y. So you can do this two ways. You can revert it and set everything back to y, or you can map it whichever way you prefer. Personally, I like to revert everything back. So I would write x is equal to 2y and x is equal to y squared over 3. And then I would flip these and I would have y is equal to x over 2 and y is equal to 3x, the square root of 3x. And then I would map these.
Always remember to take plus or minus.
Yes, your plus and minus here on your root. So there's that.
You don't want to.
Yeah, you'll miss out on half your integration. That won't be good. Or if you want, you can leave it and map it the other way. It's however you prefer. So if you do it this way, y is equal to x over 2 is just, y equals x with a smaller slope. So that's a straight line. Plus or minus root 3 is simply just the square root function up and down. And then we have other bounds of 0. So in this case, it's y equals 0 and y equals 6 initially. So you can leave those and map them as lines because these are limits, or intersections in this case. These are intersections, right? Yeah, they should be, because
yeah, it should be intersections.
So there's an intersection between the sideways root or your parabola, whichever you choose to map it as, at the origin. And then there's an intersection with the positive portion of the y equals root 3x, obviously at 6, because that's what it gives us as its higher bound for the second portion. So we have an area that has a linear bottom and a quadratic top. And then obviously it just has us, label each bounding curve with each equation. So you can just make sure to do that. And then give coordinates where the curves intersect. So you have the origin. And
wait, do these intersect at 0 and 6?
They should, right? Because if you look at the second integration, you have your bounds, right? So
yeah,
the trick is, so if you take y is equal to x over 2 and y is equal to like root 3x, the only thing that makes them equal is 0, but it does make them equal. Thereby, they intersect at 0. Like they'll both intersect at the origin.
I think I figured out my problem.
Like regardless of the portion. And then, so in this situation, the only portion of the y that matters is the positive portion. We don't need to care about the negative portion, but it's always important to keep that just in case. But it should intersect, and then it should intersect at 6 at some value. So
at 12,6.
12, yeah, 12,6.
Because 6 would be your y value. So
yeah, so it's flipped. And 12 is what? 12 is how far that half had to go to get there. Yeah, because it intersects.
Yeah, plug in y for any. Since these two intersect at that point, I would just choose the easier one, and you can double check it with the harder one.
Yeah, but if you
for
do,
example, 2y equals x would be 2 times 6.
Yeah, and then let's see if you do, and then if you do 12 times 3, it's 36. Square root that, it's 6. Checkmate. All right, so that's how we do those. The evaluating isn't that hard because it gives you what you're doing, and we're used to evaluating these. So I'm not sure if it's worth us going through and evaluating this again, since we just did a bunch of them.
Yeah.
And this looks like just more, the harder part about these questions is understanding how to reverse engineer, taking an integral and drawing its figure or its
Yes.
region.
So
But
I got something like that crap for mine.
yeah, I got a similar one, except I
Yeah.
drew mine a little thicker than it should be, I guess. But even so that's what that's about. And then we have this one.
Yeah.
Look at this. So he didn't have this worked out or requested, but he does have it circled. Find the average value of f of xy is equal to sine of this over a rectangle.
Oh, can we do one of those?
Do you know how to do one of these?
No.
Yeah, I don't know
do
what
not.
it's asking either, but I mean, we can try 19A and like work it and see what happens.
Yeah, so there is,
Average value.
it's using a double integral for average value of a function.
I have a sneaking suspicion that this means that as opposed to just doing the double integral of dy dx, this means the double integral of sine x plus y dy dx, right? That's the only way I see that sine function plugging in if it already gives us bounds. Unless there's a formula for it.
The average value of f over r equals 1 over the area of r, double integral of r f dA.
Okay, average value of a function over a rectangle or a region. In this case, it's a rectangle. All right, what does this mean? The average value of a rectangle. Yeah, so it looks like I have a function that sounds suspiciously like your function. Let's see.
Yep.
So in this case, this is a bit. Yeah. Okay. So
it's the average of the function is 1 over the area of the given rectangle.
Yeah, this is equal to 1 over the area of R. Wait, it's 1 over the area of R times the double integral with respect to R of the function. That's what I have.
Yes.
So, okay,
Yes,
so
same,
what I said at the beginning is correct, except I forgot its weird coefficient rule. So that's interesting. So the area of R is the area of the given rectangle. So we could do that via integration or simple multiplication. So it's up to us.
Simple multiplication.
Yeah, that's what I would pick too. All right, let's go back to 14.3 and look at it. So we are taking, so we get to pick. I'm just arbitrarily going to do dx dy first because I don't care. Because in this case, they're the exact same limits of sine x plus y. So since I chose dx dy first, that means 0 pi. They're the same, so you just write 0 pi for both. All right, so the area of the rectangle first, we know it's going to be from 0 to pi, 0 to pi. So our length of both sides is pi. It's pi times pi. So that's just pi squared. So our leading coefficient is 1 over pi squared. So we just have that for later. And then the double integral with respect to x of this function starts out as negative cosine of x plus y do we divide here? Do we divide by something? Do we divide by the stuff on the inside, or do I forget the rule here? Is that
So
it?
since the coefficient of x is 1, then we don't need to divide by anything.
Okay, yeah. And so we just leave
because if you want to do u sub in this, you're going to do u equals x plus y, and then du equals dx. Yeah. So no,
nothing matters
if
here.
you have du equals dx, then you can just scrap u sub.
Yeah, because I forgot, since we're cheating y, it just drops out since it's not a coefficient. If it were x, y, this would be different. It'd be divided by y. but it's not. All right, so then that's that. And then we evaluate this. So we plug in pi for x. So now we have negative cosine pi plus y minus negative cosine of just what, y?
Yes.
Yeah, so we have negative cosine.
So I got cosine of y minus cosine of pi plus y.
Yep, that's what I'm about to have. Yep. Y minus that. All right, we do the
And then
integration
that's
again.
all.
So we have sine of y.
Cosine of y is sine of y.
Yeah, negative cosine is just gonna be negative sine plus y. And then we
Negative
evaluate
sine.
this once more at 0 to pi. So sine of pi is going to be 1.
0.
0? Oh, yeah, it's 90 degrees.
0.
Half shifts. So we're going to have.
Or 180. It's
Yeah,
180.
pi's 180.
So
Pi, yeah,
sine
yeah.
is-
Yeah. So sine 0, and then sine of 2 pi should also be.
Is also 0. Did we just get a 0?
I guess the average value. Well, let's think about it. I mean, the average value of a function like fuck if I know. I mean,
Wait.
did
We
mess
have
up
to
anywhere?
evaluate it at we have to evaluate it at 0.
Oh yeah, you're right. We didn't do that. That's gonna trip it up. So sine of 0 is still 0, but sine of pi.
Sine of pi is still 0, right?
Yeah, it's still 0. Never
It's
mind.
still 0?
Never mind. I feel like the average value.
I thought.
Yeah, I feel like the average value of sine. I mean, I'm pretty sure there's nothing we did wrong here. And then obviously that's gonna be multiplied. So
Well,
let's find out if there's
we
an
have
online resource for this that could auto calculate it for us and see if it also spits out the same number. All right, the word calculator.
Or we can
autofills.
always just go to look in the back of the answers in the book.
I'm very lazy and I refuse. I refuse to go all the way. Evaluate the area. Does this even?
Let's see which one gets it first.
I suppose.
I'm looking it up in the e-textbook. Let's see who.
What does this even say? Enter the left endpoint of the interval. What does this mean? Wait, it's being cringe. It's not letting.
The average value of a function. Yeah, that's the average value of a function. That's like baby. That's like baby numbers.
Of sine x plus y. Average value of sine x plus y over a rectangle. Rectangle. There's quiz
What are we
stuff.
in? 14.3?
Yeah, 14.3.
Yeah. I already got it.
What is it?
14.3. 19.
What?
Okay, I lied. I didn't have it. It's
It's
on the
19.
next page.
I was gonna say. I
It's
thought you said-
0.
Yay!
It's 0, boys.
All right, so that's how you do that. Doubt will have to do it, but that's how you do it. Yeet. All right. 14.3
It's-
completed. 14.4 polar.
That's just something you write on your note card. You hope that you don't have to use it.
Oh, do we get no cards?
Yeah, we get a note card again.
Did you say
Yeah.
that somewhere?
Yep.
Okay.
You said it yesterday in class. Or
I
today,
missed it.
Thursday.
So note card allowed. And that's for functions only, right? Or like rules, functions, that kind of stuff. All right, let's see
Yeah.
what his solutions, what numbers we're looking for 4.
No
13
examples.
He has 13 through 17 for polar. So I'm hot trash at polar. So let's see. He said 13 through 17.
I'm there with you.
So it looks like
Yeah.
it's just these.
Okay.
So I'm gonna zoom in on these. So if we're both trash, we might just want to look at it and try and understand the solution after we try it for a second. So let's first try. Wait, what is these asking? Change the Cartesian integral into an equivalent polar integral, then evaluate the polar integral. Okay.
Okay. So
I'm gonna scroll up. Oh, and here's that average value function we just learned, but it's for the polar instead. Why is it multiplied by r?
Well,
All right. So what they did here was, they they just plugged in r and said yay.
Ickelberg. You know, I'm okay at it if it's supposed to be an integral, but it's just when it's dumb and it's supposed to be a Cartesian. Like if it's supposed to be a Cartesian and like if it's a lot easier to be a Cartesian, I know how to make it in Cartesian.
Yeah, like look at this.
But
This one's a joke. It's literally x.
13 is not supposed to be easier in Cartesian.
It is though. Right? Isn't it or no? I think
Well,
it's
yeah,
just
I'm
gonna
sorry.
be,
It's not easier in polar.
yeah, this
I
one
got it
would
backwards
just,
in my head.
this would become x squared over 2. You plug in a y, now it's y squared over 2. And then you do dy, now it's y cubed over 6. And then you plug in your numbers and you're done. But no, we want to do it in circle math because circle math cool. Oh boy. All right.
17, I get. I know how to convert that into.
Yeah, 17's cringe, but like 13 and 15, like what the heck, man? That's Cartesian all the way.
Yeah,
All right, so
17
let's,
is polar. And 17, I get that it's supposed to be in polar because it has like a square root of x squared plus y squared.
yeah.
That I know it's Cartesian.
All right, so let's
Because it gets easier if you learn Cartesian.
so we're gonna
Or
start. We're
polar.
gonna do these ones.
So y equals r sine theta.
What? That's what he did. So he
Y
defined
equals
them.
r sine theta.
Wait, so is this what we do
X
each time?
equals
Do we
r
always
cosine theta.
do we always define these as such? Is this how we
Yep.
start every problem?
Yep.
Okay. So
Yep.
I'm very bad at these ones.
And then
so
we
this is
get.
good.
So
Cool. I guess that makes sense. So there's that. So looking at
okay.
knowing that, then we can start this. So if that's the case,
So we need to first start by sketching the graph.
in polar or in
No,
Cartesian?
just in Cartesian.
Okay, that's good because I don't need to draw no circle graphs. That's all I gotta say. All right, well, looking at this, so this time, as opposed to last time, this is a bit trickier because it actually just gives us an x that isn't part of the limits. So I'm a little interested to see what that means.
I think we just ignore that.
Yeah, probably. So 0 to y but this is also a horizontal integral, so it's gonna be a bit weirder. So we can reevaluate it, but that's just y equals x either way. So yeah, y equals x.
Yeah.
And you have x equals 0, so you have the y-axis as part of that. Then you have the next one is the y equals 0, so the x-axis is part of that. And then you have y is equal to 6, and there's that. So you have an upside down triangle. Cool. There's that.
Let's see what he sketched, and is it the same?
Yes.
Let's see.
Yes, it is.
Yeah, it's second. Yeah.
Cool. Right, okay. So there's that. So now we arbitrarily just say, you know what? X is r cosine theta now, and y is r sine theta now because circle math. So I'm looking at this and I'm thinking, do we
do
have
that
to
every time?
Yeah, are we gonna have to reevaluate our limits then? That's probably a big part of this.
Okay, yes. So remember, when you're converting to polar, your dy dx turns into r dr theta. Don't forget the r.
So dy dx is r dr theta.
R dr d theta.
And then obviously dx dy. So we will be, so the r, would that stay out in front, and then we would flip the order of the dr theta, or does it not matter?
It does not matter. We always are going to do dr d theta.
So r dr d theta of the function x, which is what redefined as r cosine theta now?
Yes.
So that r cosine theta is separate from the r that's already sitting there?
Yes.
Yeah, okay, cool. Okay, so there's that. And now our integration bounds. So
and then so the outside in theta is actually easier to get. So the outside, we look at our Cartesian graph, and then we graph it. So I remember how to do this now. It's disgusting. Okay, so now we can see that it's from 45 degrees to 90 degrees
How do you see that?
based on like, okay, so we look at we look to so we look at the two angles that are made in between the x-axis. And so since we have the upside down triangle,
It
we
goes
know
from
that
45
it's
to
45
90.
degrees till we start and then it goes to 90 degrees.
So this is us
you know
going
what the fun thing
vertically.
is?
Yeah. What is it?
Yes. So we now looking for the R. And so the R is made by starting at the center and going out to your bounds.
Which bounds? So we just did the
it's going from the center to the top right. You see that purple line on my graph?
I suppose, yes. Yeah.
Inside, yeah, that's the R. So we need to get a formula for R in terms of that. So R
just to quickly
0.
understand the d theta portion. D theta, also known as like the second iterated integral, that is simply we look at our figure and we go from the bottom to the top and find the angles that change. So our first angle that's formed with the x-axis, the xy and the x and the y-axis and the y equals x line, that forms a 45 on the inside of our region. And then when you go up, you form a 90 degree from the y equals 6. So that's what we say. We say, should we write this in terms of pi, like pi over 4, pi over 2? Or should we just write it in terms of? All right. So pi over 4
in radians.
Pi over 2. Okay, so that's how you do that. So when it's your d theta, you're evaluating vertically. So starting from your bottom of your figure to your top of your figure to your shifting angles. And then looking at the r cosine theta, or the r part, the dr part, as you said, seems wacky. So let's take a peek, see.
Okay, so now it's the fun part.
Ew.
Because
that's terrifying.
Okay, so now you see how that's your theta, right in between.
Yeah, your theta. So you have to find a formula for how theta changes from that r portion. So where does your r start at the origin, like at the first angle, and then you move it along the figure?
Yes, so r starts at 0 and then it goes to some point on
the figure.
Top. Yeah, and this term it's so you do a little fun thing called if you remember about parallel lines.
Yes.
The intersection of parallel lines, they have similar angles, right?
Yes.
So I can also write this as this. We can also write theta as this angle, and this angle has the same order, same
it's
as theta. And then so we have to find an equation that connects this r to theta, but we know this because this is 6. So if we write this as a triangle.
Bert.
Oh, I'm sorry.
Yeah, so I see. Okay. So I'm going to zoom in more on this. So on this, so this is like a better, more zoomed in version of your figure. So he takes his r, which initially starts out as the line y equals x, and then he shifts it, and then he has to find the changing theta, or a relation here. So he has some arbitrary height, which will remain constant since it's a horizontal line here.
Yep.
And then he says 6 over r sine theta.
As in sine. So it's opposite over hypotenuse.
So in this case, did he simply set x is equal to 6 here, or reality, or y is equal to 6 here then?
Not.
Wait, no, yeah, he did. Look, he set for this portion, because y is equal to r sine theta, right? And here's 6, it's a y value. Plug in 6 for y is equal to r sine theta, and it comes out to be this.
that does work if it's simple. I think when it gets more complex, you'll have to think about it as more of a as what he's doing.
So
what
then
he's doing is he's making a triangle.
Yeah. So he did that,
So
and he finds some relation.
yeah. So that goes from. So the length of R spans between 0 and the full length of R, which the length of R is 6 cosine theta.
Cosecant or cosine?
Cosecant. I'm sorry. Yeah.
Yeah, cosecant theta. Yeah.
Cosecant of theta.
Yeah, that's what it ends up
So
becoming.
then we get a fun time of R squared cosine theta, and then we take the integral, which is R cubed 3 cosine theta.
Yeah, because that R
theta.
just multiplied across to the front. You do that, you evaluate. When you evaluate,
6 cosine
you
cosecant.
you get this demonology.
Yep.
Times cosine theta. You move that down, and what did he change about this? Oh, I see what he did. So cosecant is what? Is it 1 over sine then? Cosecant's 1 over sine,
Yes.
right?
So that
So
is
yes. So
yeah,
he took a cosecant out of this and multiplied it by cosine, which happens to be cosine over sine, which is cotangent, to form it like so. He pulls out his constant just because. Does u sub, what did you say the u is here? You just let u is equal to cotangent, u is equal to negative. Yeah, so
yeah, I guess so.
he
Yeah.
did u sub here to simplify it, because this allows him to just, all it does is add a negative sign somewhere on the front.
Yeah. So what he did right there is to u is equal to cosine cotangent, and then du is equal to negative cosecant
Yeah.
theta. So now you can just say u times du.
And then he reevaluated his limits as well.
Yeah, because he likes to do that, which can't blame him.
Yeah, it's fun.
It's a good habit to get into.
Yeah, because then he has that. He does this.
The cotangent of pi over 4 is 1, and then the cotangent.
Oh, and then there's something he did though. That's what I was about to ask, but I realized his negative sign. He just inverted it, caused it positive, and flipped the limits of integration to get rid of the negative sign, which is a trick I forget is allowed. And then he did his thing, replugged it all in, or more accurately reevaluated in terms of u, to just basically completely skip this. Because this is obviously so much worse to evaluate than, this. Evaluating this, and he just gets some number. So it looks like, so the most important part about the polar stuff is the beginning. The rest is simply like trig rules, which is its own topic. But the most important part is understanding the processes here. The first thing to understand is that x is equal to r cosine theta and y is equal to r sine theta is an across the board rule. You'll always do that. So this will dictate how your function changes. If it's like an x, it'll change to this. If it's a y, it'll change to sine theta instead. So that's the first step. The next step is to find your changing in theta, your outer bound. So in that case, your changing in theta, as John said earlier, is dictated by the angles that your figure forms from your lower bound to your upper bound. So you go to whatever the lower bound is numerically initially, find that angle within your region, and then you go to your upper bound to find that angle within your region. For the most part, I feel like that should be easy until you get to the I definitely don't see this one being fun. But I feel like there's probably a pretty easy thing here, because this one, since it's so obnoxious.
17 is actually easier.
Yeah, since it's so obnoxious to do in Cartesian, it probably has an easy polar representation. So
if you want to, we can do 17 real quick.
Yeah, we'll do 17 after I talk about this one a little bit more. Because then you find your lower bound figure, and you find your angle within the region. You go to your upper bound, you find the angle within your region that dictates this. So 90 degrees, 45 degrees, 90 degrees. Then for this simple figure, this is easier to find. but you go to your origin or, you know, some intersection point at one of your angles that you picked, probably the lower one's better, and this defines your R, and you define the relationship as R moves along your upper bound, whatever that may be. So that formula might change. So in this case, it was a constant value, but it gets more complex. If it were, let's say, like 6 plus X, something like that, 6 plus X, some line, then in that case, wouldn't we be setting R sine theta is equal to 6 plus R cosine theta then? If the upper bound were a line instead of a constant value here, and it had like a plus X or something on it, wouldn't we plug in the cosine theta, the R cosine theta then, and then solve for R? No, that wouldn't work, would it? Because R would drop out, right?
Think so?
Hmm.
Interesting.
Yeah. Let's see, his 17. Does he draw a figure here? His 17 is interesting. Oh, no, 17's the. Oh, he doesn't do 15, did he? Yeah. Okay, so 17 is just the one we're about to do then. All right, let's just do 17 quickly then. And look at it. So this one has bounds -1, 0, -√1 minus x squared, 0, and then of some obnoxious looking function. Dx. So the first thing that you said was always able to do is do your like the integration becomes r dr d theta. So that's something that's across the board. Then the next step here, I suppose, do we just look at this and transform it into a trig version of itself?
Okay, so what this one is actually doing is it's using x squared plus y squared equals r squared.
X squared plus y squared equals r squared. Okay, and that's a formula that's across the board.
Yep, because if you do, if we're keeping with x equals r cosine and y equals r cosine, and so if we take r squared,
oh, I see
r
what's going to
squared times
happen. That
cosine squared.
cosine sine stuff's going to drop out to become 1, isn't it? And then it's just going to leave the r squared.
Yep.
Yeah. Okay.
Yep.
Okay. So that's cool. So that means for this portion, does that just end up becoming 2 is a 2 over 1 plus square root r squared? And it just becomes 2 over 1 plus r? Or is that not how this is going to
go? 2 over 1 plus r times r dr d theta.
Yeah.
And then
that r goes on
it's going to get
right?
funky, won't?
Funky. All right.
The r goes on top. Yeah. So one of them does.
Yeah, so an r goes on top. So you're going to end up with, so to start, the function itself is going to become 2r over 1 plus r.
Yeah. So in this, we're going to graph in the polar. So in these, we're going to graph in the polar.
Okay.
And so we're going to, remember when you're graphing, ignore the inside function, and we're only graphing the limits.
Okay, yeah, every time. So graphing polar here, what does that look like for this one? So -1 to 0, does that mean we're like what values of pi produce these?
So let's first you got to convert your r into r limits into the first limits into r. So the first one, it keeps 0 on top, but negative square root of y minus x squared equals
y minus x, isn't it -√1 minus x squared?
Yes, that is.
And then that looks like what? If it's 1 minus, that's going to be r, cosine squared. As a square root.
Yep.
Doesn't that produce like r squared or something, like r sine squared or something on the other side, or what? Or just sine squared or negative sine squared, whichever. What does that translate into? Because I can kind of see what that's going to look like.
Okay, so we got a negative square root of 1 minus r squared cosine squared.
Yeah. So I know
And I
that
think
one
r is 1.
is R1.
Yes.
How do we determine that here?
Because we know x squared plus y squared equals r squared.
Mm-hmm.
And if we look, the bottom one is y equals negative square root 1 minus x squared,
Okay.
if that makes sense.
Yeah, so you square that, and that's going to be 1 minus x squared when you plug it in for y.
Yeah, so we, yes. So if we're getting it in terms of r, then let's see what he,
Yeah, let's look at what he
I think
decided.
he's done.
How do you get the, oh, he dragged the 2 out to the front. Okay. So he has this, and there's that. And he immediately is able to shift this, right? So -1 is equal to pi, and the top is equal to 3 pi over 2, 0. Why did he get to say that? That's what I'm interested in to know.
He didn't show the most important part of this.
Yeah, I'm interested to know.
Bruh.
Well, the lucky thing
Bruh.
is, what is our test on Tuesday or is it Thursday? It's Tuesday, right?
Yeah.
Yeah.
Yeah,
So
I
we
think so.
have a little bit of time.
No, I think what he did is he graphed it.
Yeah, so here's what he did. So -1 less than or equal to x less than or equal to 0, and then y less than or equal to this function, and y greater than or equal to this function, and less than or equal to 0. So it looks like it's in the lower, like Q3 of the polar coordinates.
Yeah.
When r is, as you said, r varies from 0 to 1. So you have pi and 5 pi over 2.
So let's graph this. So y squared plus x squared equals 1. That's just going to be a circle, right?
Yes. Yes, it
Okay.
should.
So but negative square root of y minus x squared is going to be the bottom half of the circle. Is that good?
Yes.
So, and then it's also just 0. So it's going to be the circle when until y equals 0 or x equals 0.
Okay, so what we can tell is, first off, the negative square root of the that like thing produces the bottom half of the circle, and then the fact that it goes to 0 tells you that when the x value reaches 0, that allows you to isolate it to a single quadrant, the leftmost quadrant of the bottom of the circle.
Think about it as in all of your limits, because you got so you got the limits between y and something and 0. That gives you the bottom half of the circle. Yeah, I misspoke earlier,
and then
but it gives you the bottom half of the circle.
Yeah, and then
I see that the x limits gives you the second half, gives you the half on the left hand side.
Yeah, because
because from -1 to 0 is going to be that.
Yeah, because when r has a value of -1, it's to the left, and then if it shifts to 0, well, this is when it's in terms of that's when it's in terms of the x-axis. So when x has a value of -1, that means r is on the left side, and then when x has a value of 0, that means r is along the negative y-axis. And then, as you said, the next portion, when we're working with the y varies along that -1 minus x squared.
And that's what gives you the circle.
And that's what gives you that mapped value. So that maps the line.
And that negative means it's the bottom of the circle and not the top of the circle.
Yeah. Although that definitely could, you could tell that from the first part, kind of, right? Because if Oh wait, no, you couldn't. You're right. That's what describes it, because if you work off of only the outer limit where it's -1 to 0, it could be the left hemisphere as opposed to the right hemisphere.
Mhm.
And then the next portion limits it to the southern portion of the left hemisphere, even though this
Yep.
is a circle and not a sphere.
Yeah.
That's how it would be.
It could be either the left of the half circle or right of the half circle based on x. And that's
Yeah.
what -1 to 0 gives us it being the left hand side, and then the negative gives us the bottom hand.
All
And
right.
the y integration tells us it's going to be a circle.
Okay.
So and then fast forward here, he just says that now that he's getting his circles right, the integration is between 1 and 0 and 3 pi over 2 and pi.
Yeah, because what? Because a circle's values go from 0 to pi over 2 to pi to 3 pi over 2 to 2 pi. So our bounds for the angle are pi to 3 pi. Okay, so when it comes to polar, it looks like graphing is the most important part, because that's what's going to allow you to find limits.
Yeah,
And then and then manipulating the function is secondary to that.
Yeah.
Although not necessarily 0, because then you look at this, because what we got, because we immediately were able to tell that you can replace everything and it just reduces and becomes 1 plus r in the denominator, because when it comes to simplifying the inner function that has nothing to do with the limits, it's simply plugging in the x and y rule, or using the x squared plus y squared equals r squared rule, whatever you need, and then multiplying that r across to the top, which we did.
And you can, yeah, so there's 4 main functions in converting from polar to Cartesian to polar, and that is x squared plus y squared equals r squared.
Okay.
Y equals r sine theta,
Yep.
x equals r cosine theta, and then finally, let me make sure I'm right, y over x equals tangent theta.
All right, so that sounds like 4 functions that need to be on your cards, people. That's all I gotta say.
Yep.
All right, so really now that I've had it explained, it seems like the most important part is the graphing, and the rest comes secondary because it's pretty much plug and chug.
Yeah.
And integration rules.
And here, yeah, here's what I got. I think it's mirrored.
That your functions, that is?
Yeah. Is it mirrored for you? Yeah.
No, it's not actually. I'm pretty sure the software flips it so you can read text, which is clever. So I think it mirrors it, which is funny. And when he evaluated, he got some number. But evaluation, as far as I'm concerned, for the polar comes secondary to understanding this portion. This is the most important part. All right, so I'm gonna stop us there for polar, simply because we have like I think, is this 14.4? Yeah, we got to do 5 and 8, and this is the triple integrals. But this is just a higher level application of this stuff.
Yeah.
Although I think this is the Jacobian.
And of course, polar is worth the least amount on this test.
Yes, that is another thing. So if we go to this quick test breakdown that he sent out, polar is evaluated at the least quantity. So you can afford to make some mistakes there if you had to pick. Although,
yeah,
you don't have to pick. But so we put the most time for this portion, for this study session, into this, obviously, because it's pretty important. But even so, all right, let's get to 5.
Polar, we spent enough time on polar, because
for
polar
what it
is
is.
the least amount, and to really understand polar, you will have to put hours.
This is what I'm confused about. Why is this 14.4, 17 to 19, and then 14.7? Does he not have solutions for everything? Unless they're under this portion. Let's look.
I guess he.
It looks like he's out of. Let me look at this and see if. No, it still looks polar. Yeah. All right. Looks like these ones were on our own, but that's not too bad. Triple integrals isn't the worst in the world. I'm pretty sure we can confirm if they're right.
And I also have it the answers pulled up in the back of my book. So
Yeah, that's also good. All right, so let's look at how many there are here. So we'll pick like these things can be a little long, so we'll pick 2 of these. So I say he's probably most likely to do something like this and something like this. I feel like he's less likely to do ones like this. Like the right, actually, no, I don't know, because we've done a collaborative where we had to write 6 different iterated triple integrals given like something. So here, let's just start with let's just do number 3, and then we'll pick this or this.
Okay.
Or another one. All right. So number 3, volume of the tetrahedron. Write 6 different iterated triple integrals for the volume of the tetrahedron cut from the first octant by the plane 6x plus 3y plus 2z equals 6. So tetrahedron.
And also correct me if I'm wrong. He said that he will give us a visual for this.
Oh, did he say that?
He does not expect us to. That's what I remember.
Oh,
Is
well,
he
screw this.
said
We're not
he
doing
would
number
always
3.
give us.
We're not doing number 3 then.
He will always give us a region. Like number 24, if you look at number 24, I just saw it flash by. He'll give us something
25.
like 21, 24, 25.
Yeah, any of these.
Something
Yeah.
like that.
Okay. Yeah, because this is scuffed.
Very,
I don't want to do these. I hate these so much. I hate like having to figure out the figure. Particularly when it comes to dimension, like 3 dimensions, there's a lot more room for error for a figure. All right. Then we'll do one of these and one of these. So we'll do a basic evaluation of a triple integral, and then we'll do this. Although I would like to do.
So
here, what we'll do is we'll do one of these, but even though it doesn't ask us to rewrite the bounds, we'll rewrite the bound. Oh wait, never mind. We'll do 21 then, because rewriting the bounds is definitely something he'll make us do. All right, we'll just arbitrarily pick number 7 to do. All right. So when it comes to simply evaluating these,
if we're gonna do any one of these, we should do something we should do number 15.
15 then? Oh yeah, 15 looks trickier. Oh yeah, because number 7's really easy in comparison. 15's one we're more likely to see. Yeah. All right, 15.
Yeah.
There's number 15. I'm gonna numb it. 2 minus x.
Because
yeah, the other one's like nothing. Those things, we could churn through those all day. It's just like, it's basically partial derivatives, but the opposite. Partial integrals, which is basically what I've been calling this in my head. I don't know if it's something you should be allowed to call it, but that's what I call it. All right, so number 15. The order is dz dy dx. Thereby we start, and it literally just produces, 2 minus x minus y right off the bat. The next step is integrating with respect to y. So across the board, you do 2y minus xy minus y squared over 2. And you evaluate it by the limit 0 to 2 minus x, and then you plug and chug all the way through. So we get 4 minus 2x minus 2x minus 2x plus x squared. Then we get this, which is going to be minus x squared minus 4x plus 4 over 2, and all of that will be negative. These ones are tricky because the algebra gets a little wacky. So when I do these on paper, I abuse parentheses to no end.
Oh yeah.
Absolutely. All right, so looking at this, so I see what this is going to form, so I can do my sign flip that I do across the board. So first things first, yay, that number 4 drops out. Don't need to, never mind, I don't get to say that. No, I don't. Forgot to divide. We have the number 2. And we have minus 2x.
Oh man.
And then we have plus x squared over 2 as opposed to minus it, because that's how that goes. Then the last step of this is to evaluate from 0 to 1 after integrating it once more to x minus x squared plus x cubed over 6 from 0 to 1. So we have 2 minus 1.
Hearing what you said, I think we got the same thing.
1, 6. Yeah, let's see. 1 plus 1, 6. It's going to be 7 over 6. I have 7 over 6 at the end.
2 minus 1, 1 plus 1, 6 is
7
7
over
over
6.
6.
Yeet.
And
all
that is
That.
what question? 15 on
15, 14.5. Page 7. The
Yep.
question's on 785. Is it 7/6?
Yep.
Yeet. All right. So quick, since basically all we did was we just sped through that without saying too much. The description of these ones. So there's a reason that we chose to do 15 as opposed to doing 7. The difference between these questions is here you're given an underlying function to evaluate as you take the derivative, you take the integral of each part. Like since you start with dz, you take only the integral of this. Well, you take the integral of everything, but you're taking it with respect to z. So this becomes x squared z, y squared z plus z cubed over 3. And then you'd evaluate it, plug 0 in for all z's, and that cuts it, plug in 1 for all z's. And then you're just going to have x squared plus y squared plus 1/3. You do y, you do the same thing, y, x squared, y, and then all across the board. So this is easier than these types, which are more common. These are the types we'll have to do more frequently, where your bounds up until the third are functions. And these functions will be essentially generated. Like if you have dz as the start, this function won't have a z. If you have dy as the second, the function won't have a y, that kind of thing. Dx will be your limits. And that's what we did. That's why we chose this one.
Yeah.
And because all of these
and 15 is also what you would get if you are calculating the area of a
volume, right? Volume.
Three-dimensional. Yeah,
Area,
a volume of a three-dimensional.
Yeah, so 15 is like what we're more likely to actually have to do. If you are given one of these though on the test, be happy. They're relatively easier to do and evaluate since you're evaluating as you go, as opposed to evaluating some chunky function at the end. All right, so that's 15. So now we'll pick 21 to do since we have to rewrite integrals orders, and I know that's going to be on the test. So we're given to start -1 to 1.
Wait, isn't 21 what we did for collaboration?
Shit, you're probably right. All right. Should we just pick one? Should we pick one and then just make ourselves rewrite it like twice? Yeah, let's just do it that way.
Yeah,
since by the Fubini and all the rules and everything, we can rewrite any given one of these in 6 different ways. So do you want to do the weird looking pyramid, the wedge, the door stopper, the skateboard ramp, or the shitty triangular pyramid?
I hate this. I hate the 27. Can we do that for collaboration as well?
Probably. I don't know. Maybe.
Didn't he just like shove like thousands of collaborations down our throat at one point?
Yeah, no. Before in preparation for this test, we've had quite a lot of collaborations. I understand why, but just because of the nature of online and like if this were a classwork collaboration like we did like last year in Cal 2 and Cal B, it would be much better for all of us involved because you're in class, you're forced to collaborate. You get in the groups and work and like people can explain to each other. But since we're all online, people are more likely to just try and do it themselves as opposed to actually grouping up unless you're actually doing it in class. But because of the nature of, like half of us are in class or required to be in class at any given day, it ends up where the students who weren't there probably almost always exclusively end up doing it alone. I know almost every single time, whether I'm in class or not in class, I do it alone just because I work faster. But the problem is some students, they're not going to work fast. They don't understand it, but they're not going to ask for help simply because it's a more effort than if they were in a group already. Like they have to go contact. There's a lot of anxiety with regards to that. So I kind of understand it. So the collaboratives, they don't translate well into the online environment as far as I've seen thus far.
I would
unless
agree
you're
with that.
unless you're forced to do it in class with other students via breakout rooms, which he's done before. But the reasoning why that wouldn't work totally here is, as I said, for this class, we're only required to be there half the time. So half the students who don't attend will always be out of the loop there. So
Also, 21 was 10-15 collaboration.
Okay, good. All right, we have to pick one of these then. One of these ones on the side. So you said you hate 27. I probably hate 27 too, because this looks like Garbo. But
do you understand what we have to do here?
yeah, because I think we have to do this on a homework assignment.
Yeah.
One of these.
So what we have to do is we have to find the equation of the plane.
Oh, well, I remember how to do that. Okay, well, never mind. We're not going to do that. I don't want to touch that right now.
Because we're going to have to. The reason why I don't like it is because we're going to have to take the cross product of two vectors that we make between the thing to find the equation of the plane.
So what? We would arbitrarily define a
vector.
vector. I would just pick from here to here, from here to here. I'd take the cross product, and then you take the normal vector of the cross product. You have your equation of a plane, and then using your equation of your plane, what's the next step through there after you've bound?
To find the normal equation, you
well, I know I know to define the normal thing that gives you the equation of the plane. So once you have the equation of the plane, what's the next step past that?
So that's going to be your endpoint for your z. So if you see what I'm saying, dz is going to, your limit for your dz is going to be from 0 to that plane function. So and then dz will probably be first, or actually dx, dy, and then probably dz. I don't know.
I think in this case you can pick.
Yeah.
You can always pick, actually, unless expressly told otherwise because of Fubini's theorem and the rules. But so doing that, so let's say we start with dz. Does that mean we would zero the z portion of the plane equation, or do we do it another way, or do we just integrate that portion of the equation?
We solve for z.
Well, our bounds are pretty solidly given. Like our bounds for the z-axis, it's going to start at 0 and it's going to go up to 3. And we're going to start for x. If you enter this figure, it starts at 0 and goes to 1. And y, if you enter this figure, it starts at, well, I mean, that's the extremity bounds. If you go up inside to find your z bounds, you're going to always start at 0 across this portion, but you're, depending on where you entered, it's going to hit the equation of the plane, right? Yeah, so that's what so the equation of the plane's used for all of them. Because you're always hitting the plane, regardless of which direction you go. Okay, I understand what that's saying. All right. Well, in that case, let's just, he circled 25. Let's just do 25. All right. So we have the plane y plus z equals 2, and the cylinder x equals 4 minus y squared. So we'll write this two ways. So I'll pick the first way to do it, and then you can pick the other way. So I'm just gonna say our first one, we're gonna want to order dz, dx, dy, and then you can pick the order you want to do it after that one. We'll do it twice to
so
demonstrate.
We're doing 25.
Yeah, we'll do 25. All right, so looking at this, so our upper limit for our z looks like it's the plane, right? Is it? No, yes, right? Or no? So the cylinder.
So what these are. So if you got anyone who wanted to, this troubled them, it's the 14.5 homework that was due on Wednesday.
This one?
25? Yes. That was question number 3.
Cringe. Yeah, we're just
with
gonna
different
look at
numbers, but yeah.
Yeah, all right. Let's look at this one anyway, just to have a version of it recorded, because we're almost done. Because in this last one, we'll probably do like one example. Because he actually had us do this one on the homework. But let's see. So we'll just do 25 once. So if we wanted to evaluate this in the order dz, dx, dy, we have to set up our bounds, and that's basically all we're doing. So we're given two things. We're given that y plus z is equal to 2, and we're given that x equal to 4 minus y squared. So if we're starting with z, we want z to be equal to something. And we don't have any description in terms of the z portion. If we were to project xy onto the z, there isn't a constant like portion here, so it's going to be a function. And if we look at the functions we're given, only one function contains z. So if you set z, if you isolate z, you have 2 minus y. So I think our first bound is from 0 to 2 minus y, right? Enter from the bottom of the figure, go up through the top, and you'll always hit across that line between the z and the y, right? Because that's always the chopping point across, since that's the plane, right? The cylinder is the general figure, and the plane is slicing through the cylinder and creating an isolated area. And everything else is bound by the octants. So that slice that looks like it like slices and curves up is actually a straight slice across the top. It's just drawn stupid. So looking at this, I see that if we're going through, when you're trying to find, like if you're trying to find dz, you are seeing how it changes along the z. If you're trying to find dx, you're seeing how it changes along the x, that kind of thing, right? The bounds.
Okay, so with this one, you're going to want to make it in terms of dz first.
That's what I said, or that's what I just arbitrarily picked it, but I guess dz makes the most sense to start, because if you look at it, you're given that plane formula, and I just said earlier, like if you start with something, you want to have the isolated variable. So you do z is equal to 2 minus y here, if dz starts as the upper bound. If you enter from the bottom of the figure, which is going to be 0, and go to the top of the figure, the top of the figure is always going to be at any portion arbitrary, like regardless of where you enter the bottom of the figure. Go through the top of the figure, it's always going to be along that plane, which if you're isolating it and saying, oh, well, now it's z is equal to something, you can treat that now. It's always going to enter a line that's between z and y, and that line is y minus 2. I think. I'm pretty sure that's how I would do this, or start it if I start with dz. Because go up to the bottom of the figure 0, and you're going to approach the plane. The plane being set equal to z is going to be 2 minus y. So our first bound is 0 is equal to 2 minus y. That means that our next portion, you want it. So should we do dz dy dx here then? Or should we do dz dx
I did dz dx dy.
Yeah, because then the next one, that means that you can just doesn't the next one mean dx mean you can just plug in 4 minus y squared then, and then just find your lower bound, which also happens to be.
So if you think about it, we're going to project the region onto the xy plane. And so now we're going to start by, if we're going to take it in terms of dx, we're going to start by going in on the right side, and we're going to go in at 0, and we're going to go out at 4 minus y squared.
Yeah,
that makes sense.
You enter on that side, the far side, and exit the. You enter the far side and exit the close side along that curve of the cylinder. So the far side is just the 0; it's constant across any portion of the figure, and the close side along the curve, if you were to project that linearly into a Cartesian set of coordinates, you'll see the parabola 4 minus y squared. So our bounds are going to be 0 to 4 minus y squared. And then our last portion is our dy, which has to be linear numbers here is what we're looking for. So we're
now
for an intersection point, right? For our, well, it starts at 0, and then
I think I did it dz dy dx. I think I did dz d. No, I did it in dx.
Yeah, it works either way.
So now we're going to
yeah, we have to find the northmost.
But is it? But okay, so what are our bounds in though?
Yeah, so I feel like this one has to be, should ideally be done as dz, dy, dx, right? Because x actually has solid bounds. Does it even?
I mean, so does y, doesn't it?
No, y does have solid bounds. Yeah, no, we're fine. Because look, it just goes from 0 to wherever it's 2.
Two?
It's 0 to 2. It's wherever that
Zero.
plane function is equal to 0. Whenever z is equal to 2 minus y is equal to 0. When it intercepts
Yeah.
the y-axis, that's a constant value. Because we're tripping
Yeah.
ourselves up because we're looking at the variance along the x-axis and thinking that we can't use it, even though we're only caring about the y-axis here.
Yeah. And I mean, we can use, so we're going to plug in 0 for either x and y and try to get what the y coordinate is, because that's what the y coordinate is along the y-axis.
Yeah,
So
and
we
if you
can
do
choose
that,
either either equation and 0, plug in 0 for x and z.
Yeah, so if you were to
So
flip
the
it and
easiest
say
one
dy
is y plus
dx,
z equals 2.
yeah. If you were to, and now looking at, if you were to choose the opposite way and choose dz dy dx, then you can also find your x value by plugging in 0 for y, and you'll get x is equal to 4, which sounds about right here. So now let's evaluate this one quickly as a demonstration. So your first one is just going to spit out y minus 2. Then
2 minus y.
Oh yeah, and I miswrote that. Beautiful. All right, 2 minus y. 2 minus y, evaluate that or integrate that with respect or adding x's, you'll get 2x minus yx, plug in your numbers, and you'll get 8 minus 2y squared minus 4y. 4y.
Plus y cubed.
Yeah, plus y cubed.
dy
cubed. And
from 2 to 0.
Yeah, and then we have to integrate this. 8y
Oh goodness, this
minus
is
2y cubed over 3 minus 2y squared plus y
my pen
the
is dying.
fourth over 4 evaluated from 0 to 2. You have
All my pens are dying.
16 minus 16 over 3 minus 8 plus the fourth is still 16 divided by 4 is 4. So we have, this becomes 20, that becomes 12. 12 minus 16 over 3, I can turn that 12 to 36 minus 16 all over 3 produces 20 over 3. We'll have to look this up to see the answer.
Do you have an answer for it?
I have 20 over 3 is what I got.
Okay.
Because did you get the function 8 minus 2y squared minus 4y plus y cubed before integrating and evaluating for the last portion?
8y minus 2/3 y cubed minus 2 y squared plus 1/4 y to the fourth.
Yeah, that's what I got when I integrated. And then when you evaluate across, it produces a bunch of numbers. So the first one goes to 16. Okay. The next one goes to 2 times 8, which is 16 over 3. So negative 16 over 3. Then you have 4 times 2 produces 8. Then you have y to the fourth, which is going to be 16 divided by 4 produces 4. Add all your integer numbers and you will get the number 20. No, you'll get the number 12. And then multiply 12 by 3. You'll get 36 over 3. And then minus 16 over 3 produces 20 over 3.
And that is the answer in the back of the book.
Baba Yaga. Cool.
Baba-da-baga.
Bibbidi bobbidi. All right. So I'm not going to, at least we probably, for time consideration, we probably won't work through another full version of it. But if we were to rewrite this in terms of a different one real quick, let's change the first one arbitrarily. And we'll just say we're going to do dx, dz, dy now. Let's just write the limits for this one and think about how we would. So now if we're looking along the x-axis, if we're looking along dx, we're looking for something that varies with only x, or something that's like set equal to x. So if you project the figure onto that next existing plane that still remains, And if you enter along the x, you'll enter, and your lower bound will be that 4 minus y squared. And your upper bound, wait, is it, oh shit, I'm going inverse, aren't I? It's 0 to 4 minus y squared here for the first one, if we chose dx first, right?
If we choose the x, we're going to project it on the zy plane, so it comes in 0 and then comes out 4 minus y squared.
Yeah, okay,
you're right.
All right, so that's what this is 0, 4 minus y squared. Now let's do dz was the next one I decided just randomly. So now if we're coming along dz, if you project it along the y-x plane, you enter at 0 again, and you raise up to, once more, it's just going to be z minus y here. Right? You enter at 0.
Z equals 2 minus y, right?
Yeah, 2 minus y, 2 minus y. So you enter at 0 again, and you'll reach 2 minus y. And then the last one is dy, which is what we did last time. I should have flipped it up completely, but either way, it's still, your projectile is going to go to 0 to 2 once more. So every single time you rewrite it, it's not like you can write it once and then just shift the integral order around. Sometimes that's the case, but not always. In fact, most of the time it's not the case that you could just, because in this case, we got lucky with this figure, and you can simply shift the order of the integrals around and there's not much change. But sometimes if you like, and you change around and you go like, if I put dz where dy is, like the function and the numbers could change completely sometimes. And it's very important that you keep track of that, because that can be a problem. So it's always best to rewrite it and reevaluate the figure yourself, as opposed to just guessing and checking and assuming that you can just shift stuff around. But now it's time for the magnum opus, Jacobians.
Jacobians.
Yeah, so,
Okay.
on his topic thing, he says Jacobians are worth 20%, and the other stuff's worth 20%. So if you want a guaranteed, wait a second. What's this guy's math? We're missing some portions, aren't we, right?
Well, no, it's 85. 85% of the test. We're only getting 85% of the test. What's the other 15, prof?
I'm confused now.
Where? I didn't notice that before, but yeah.
Oh well, I guess the other 15% is just free points. All right. He said 14.7.
You know, yeah, get a free 50. Why not?
Yeah, we just start out with a 15.
Jackson, what you doing?
All right, Jacobian and transformed
regions. Let's see if I email.
If you email him like, yo, bro, it's another 15% of the test. I'm terrified. I mean, he did say approximate breakdown, but who knows? All right. This last portion. So we did number 6 already. And if I remember correctly, so what did he give us? He gives this, 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 and this. So we have to find the bounds of the region. And then we have to use the transformation that he said, which is up here. Where is it? Come on, where are you hiding? This is an equation we're probably going to want to write down somewhere. He starred this and starred this. Because beforehand, where do we start? He talks about Jacobians all over the place. So let's just do a couple of these, or like 1 or 2 of these. So look, we did number 6 already, so we're not going to do number 6. So let's look and try and do number 2. Number 2a. Let's look at 2a and see how this is done. 2a. So we have u is equal to x plus 2y, and v is equal to x minus y. For x and y, solve the system for x and y in terms of u and v, then find the value of the Jacobian, which is the partial xy over the partial uv, which I believe, since this is 2 variables, would be done using the square determinant 2 terms. Is that right? No. Yeah, isn't it a partial x over partial u, partial x, partial v, partial y, partial u, partial y, partial v, and then it's the determinant of that. And then that produces a matrix or a determinant, and then that evaluates stuff. So I need to see, I haven't seen any examples done of this because I'm not sure if I was available for that class. So I remember doing this because I had to look up like the process of how to do transformations and then figure out how to do this one. And this is using some region bounded. So let's
Okay,
see. I
so-
have the ability to pull up my past assignments. And I can go to this and this. Is this the Jacobian one? Yes, yes it is. So this is the one that he made us do as a collaborative. So
yeah, the J equals the partial with U partial.
this one.
You see that? Yep.
So that's how that goes. Yeah, so I was able to remember that it's the determinant of this, and then this just produces a bunch of numbers. So, and then we have to do something over here. Because this is a formula that we end up using, but where do these bounds come from? That's what I'm interested in hearing. I got them from these formulas, right? That's where I got them.
Yes. So if
Yeah, something over here is where I did V low, V high, U low, U high is how I defined these things. And I believe I got these from up here. Where did I redefine these things by? V low is -1 and I had V as secondary.
I don't need to know that. Realized it wasn't. Okay, so yeah. So what's the question now?
We're looking
I'm back on
for
track.
Bob. We're just gonna do number 2. Where it gives us
Okay.
2 formulas. It says solve the system for x and y in terms of u and v. Does this mean we have to rewrite these things?
Okay, so I need to pay attention. Okay, so are we doing 2 or 3? 2?
2A. We're just gonna do 2A for this
2,
one.
Okay, 2A. That's easy dubs. Okay. Why do my pens die on me? That's
My pens die constantly and I hate it.
there we go. I love writing in pens, but they die constantly. Okay, then find the value of the Jacobian.
So it first wants us to solve the system for x and y in terms of u and v. So it wants us to rewrite these formulas, I think, first. So it gives us one for v, one for y. Yeah, v, one for u.
If I'm right, yeah. So we got to find x and y in terms of u and v. So that means we need
we can make a single function out of this, right? Out of these 2 to make this happen.
If I'm right, we have, what we have to do is we have to add and subtract them to, so for example, this is like a linear algebra crap.
Oh, so what we're gonna have, all right, we can do x pretty easily. So if we multiply
U minus v.
Yeah, u minus v. So we would have u minus v is equal to, that's going to be 3y. So then u minus v is equal, or u minus v over 3 is equal to y. And then if we cancel everything to create x, that means we would multiply the v function by 2 and then add them together. So we would have
u plus 2v equals
is equal to x. All right, so there's that. That's in terms of
4x.
4x?
U plus 2v equals 4x, right? And 3x.
3x. So then we divide everything by 3 once more.
So
there's that. So we have x and y in terms of u and v now. Check. So now we have to use that to find the Jacobian. So okay, so we have to okay, I remember. So here's how you do this. You set up your determinant, which is the partial of x over the partial of u, then the partial of x over the partial with respect to partial v, then partial y with respect to partial u, partial y with respect to partial v. And then you do this across the board. And you go and you do that, and you're going to get partial x with respect to partial of x with respect to partial of u is just going to be 1/3. 1/3. Partial of x with respect to partial v is just going to be 2/3. Partial y with respect to partial u is going to be once more 1/3. And then partial y with respect to partial v is going to be -1/3. And then determinant of that's just do the thingy, and you get -1/6 minus.
Wait, -1/6.
Well, if you multiply, yeah, I added. Ooh, what do you know? All right, yeah, -1/9 minus -2/9. Yeah, -2/9 is going to yield you -3/9, which is -1/3, right?
That's our Jacobian. Yep.
Is that it here, or what does it want?
That was a dummy. And
Here, let's see. This is what it says up here.
oh, it's my A textbook. So
It's got a formula. This is if it had all three variables, but we're doing this one.
3x3 determinants.
Yeah, I mean that's just that process where you do, determinant of these multiplied by that, determinant of this and this multiplied by that, and the determinant of these multiplied by that, and then this central one is a negative of itself because of the sign portion. That's linear algebra rules and cross product rules though, so it's it's how it be sometimes. I have a feeling that he's not going to make us do the Jacobian of a polar because he squared this and he didn't. He didn't, and I don't think a single example he's circled here is polar. Yeah. Yeah, not a single. Like here are the ones that are obviously like probably going to end up polar, right? This one definitely.
Yeah. Okay, so what number 2 on 14.8?
2A.
I forgot. It's not an odd, so it's not in the back of the book.
Cringe. Oof. Although when finding the Jacobian, let's see how much farther I took it on my homework. We found, see, this one also happened to be -1/3, which is really interesting. But oh well.
Is this the same problem?
No, because look at this problem. This is this. It just so happens that x and y end up being the same thing. Don't know why. Because let's go to 1408.
Wait, scroll up a little bit.
On this.
Oh no, yeah. So U and V are just closely related.
Yeah.
To these two. So U is gonna be whatever. So you're gonna factor the top one and then U and V.
Bert. So on this one, we solved the system, but then it has a B portion that says find the image under the transformation of the triangular region, and then it gives you the regions. So if we were to do the B portion along with it, it would be us defining this and with this information. But yeah, so it's almost 11 o'clock at night for me, and for you it should be almost 10 o'clock at night.
Yeah, it's almost 10 and I have.
So we're gonna wrap it up.
Yeah.
Obviously, this was posted several days in advance of the test, so if there's any more questions or stuff like that, people can ask in the general chat and such. People are asking me for questions.
Yep.
Yes, good sir.
I will. Okay, you are recording your DMs, by the way.
I know, but every single one of these is literally just people asking questions and suffering, so that's how that goes.
No worries.
None of my DMs are sus. I'm not a sus man. All right, I'm gonna stop the recording. I'll stop share.
Yeah.
Then I can